and thank you for tuning in to my presentation today on supporting lung protective ventilation using predictive analytics in intensive care units using high-performance computing. My name is Rachael Hagan, and along with my supervisors, we have carried out this work at Queen's University Belfast. This work originated from the VILIA alert system, in which patient ventilator settings are recorded in real time. If thresholds were breached continuously for a period of 60 minutes, the clinicians are alerted to intervene. This research turns focus on predicting these alerts in order to give clinicians enough time to intervene and prevent the breaches from actually occurring. Mechanical ventilation is a life-saving tool that allows for respiratory support. However, injurious ventilation frequently occurs when high tidal volume values are delivered to the patient. Tidal volume being the amount of air delivered to the patient's lungs during mechanical ventilation. The idea being that too much air will cause damage to the alveoli. We can think of this like a balloon. When too much air is delivered, the balloon is damaged beyond repair. We know from the literature that tidal volume should be between 6 and 8 milliliters per kilogram of predicted body weight. A clinical decision support tool that predicts these threshold breaches will decrease mortality rates and allow for better utilization of ventilator resources, which is highly important in current situations such as the COVID-19 pandemic. For each of the minutely tidal volume recorded profiles, we take 15-minute average bins in order to smooth out the random fluctuations in the data. These can be due to sensor errors or even patients moving in the bed. We aim to predict tidal volume 1 hour ahead in order to give clinicians enough time to intervene. We further use the Python TS-Fresh package in order to extract features from our time series as input into our predictive models. We first look at using regression techniques for prediction. We compare multiple ensemble learners in which multiple predictions are made using decision trees and combined in different ways in order to get the greatest accuracy. We further compare long short-term memory neural networks for the prediction of tidal volume. We utilize the Kelvin supercomputer to train our LSTM models, and we use 20 input points to predict 4 ahead. First, we tackle the problem of predicting 1 time step ahead, i.e. 15 minutes. We report the RMSE and the time taken for all computations to be made. For RMSE, we take the smaller, the better. We notice here that AdaBoost regression gives the best trade-off between RMSE and time, and therefore we proceed with this method. Here we can see that predicting up to 4 time steps ahead using AdaBoost regression increases the RMSE slightly from 0.69 to 0.74. However, this is not much of a decrease in accuracy. Further, we compare 2 LSTM models, one with 1 layer and the other with 3. We find that increasing to any more layers increased training times to up to 24 hours, which is just not viable in such a clinical setting. We can see that the RMSE is increased dramatically, so we conclude that AdaBoost regression is the best predictor for this particular setting. We therefore explore how well our model can predict the actual alerts recorded by the VILIA alert system. For the 84 alerts recorded for this particular patient, 81 of them would have been predicted 1 hour ahead, and therefore could have been prevented. We report a probability of detection here for 0.96. In this talk, we have demonstrated the viability of machine learning methods for the prediction of tidal volume to aid in lung protective ventilation. Going forward, we aim to include more physiological parameters in order to get a better understanding of patient states. We further would like to explore parallelization to decrease the computation times and explore the scalability of our models to working in real-world scenarios. Thank you for listening.